Hi everyone, thank you for joining the Surpac session today. What I want to cover is how we can make use of Python from inside Surpac. So the goal of this session will be to show you the various ways that we can do that. And there are potentially three different ways we can go about utilizing Python from inside Surpac. But before I jump into that, what I want to do is just briefly touch on what we can do inside Surpac at the moment and the architecture of Surpac with its macro language. So if you've utilized macros inside Surpac before, you will know that it uses TCL or Tool Command Language. This is a widely used programming language in a lot of different industries. On top of TCL, we have built our own set of functions called SCL. And as part of that, we have something called Guido, which is all our forms. And on top of that, we have a Java interface where we actually use Java to display all the menus and toolbars, and also all our charting is all done with Java. So I'm going to show you how we can utilize Python to do some complex mathematical operations and improve some of the geometry functions inside Surpac, and also how we can use Python to get some nice charting out as well. So a combination of those things will hopefully give you a good overview of Surpac and Python. So for this demonstration, I'm going to be using Surpac 2025 Refresh 2. And what that allows me to do is to drag and drop Python files into Surpac and run them, .py files. But before I can do that, I need to come into my customized default preferences, and you'll see here that I actually have an option to set the Python path. So this version of Surpac will allow you to set the Python path, but it won't actually install Python for you. So as a user, you come in there, once you've installed Python, you nominate the path to where Python is, and then from then on in, you'll be able to drag and drop Python files. Now we have several ways of executing Python from inside Surpac. One of the ways that we can do it is by wrapping Python code in TCL and then executing Python when we need to. Another way that we can do it is to just drag and drop a py file directly from Surpac and execute the Python script that way. Now when you do that, there's a couple of different variations that we have. One of those is to actually have data and variables inside a CSV file or some sort of file. The other variation of that is to actually utilize some new SCL commands that Surpac has introduced in 2025 Refresh 2, which allow you to pass variables from TCL to Python inside a macro. So I'll demonstrate both of those, and I'll start with the TCL wrapping of Python code. So let's dive into the first example, which is wrapping Python in TCL. And I think one of the best ways to demonstrate this is with the problem statement of expanding a boundary. So if I do this normally inside Surpac and expand this boundary string 160 meters, you can see that Surpac has expanded it okay, but you can also see that where the corners are, the actual distance is greater than 160 meters. So that's one of the issues. And up the northern end of this polygon, you'll see that it hasn't quite adhered to the geometry of the shape either. So one of the things that I've done with this particular Python script is used a library called Plotly, and that's very good at doing, Shapely. It's very good at doing polygon intersections, outer sections, and expansions. So same distance, 160 meters. You can see that the northern end has expanded the geometry correctly. And if I run out the distance there, you can see that from the corner to the expanded boundary is exactly 160 meters. So this is very useful for things like blast boundaries that are often required to be at certain distances. The other thing that Surpac does when it expands, or in this case contracts, is it doesn't have the ability to contract and form multiple polygons. So if I contract this shape by 60 meters, you can see here that it's contracted it okay. We've got the same issue on the corners, whereby it's not adhering to the distance. But there should be a second polygon in there that's created. So the Shapely library is able to contract this by 60 meters, and you'll see that it actually does form the secondary polygon up the north there, and it's adhered to the geometry of those corners as well. So there's 8.1 and 8.2 is my second segment there. So there's several reasons for using Python in this instance, and the Shapely library is very good at doing this sort of thing. So now that we've seen Python in action to expand this boundary, let's have a look under the hood to see how it's actually been done. Now this is the first case that I was explaining before, whereby Python is actually wrapped in TCL and run using TCL. So if I edit this one, we come into any text editor, but I'm using context in this case. And you can see the first part of this macro here is all TCL, and this is how we create new points in TCL. Well, these are actually SCL commands. Now, the next part of this is a form, a Guido form. So this allows the user to enter the distance and the string number that they want the expanded polygon to be created in. Then we're using a TCL while loop, so the user can select as many polygons as they want to expand. And from line 51 onwards, you can see here, this is where Python starts getting involved. So I'm using a set Python script variable, which is TCL. And then what I'm doing is I'm building a Python script line by line, but wrapping it in this TCL here. So this is all going to be stored inside this one variable called Python script. And about halfway through writing this Python script, I'm pausing it and allowing the user to select any segment they want to expand or contract. Now, that will display the form. They can then choose the expansion distance and the string number they want to use. And then this bit of code here allows TCL and SCL to iterate over the points on the segment that's going to be expanded. And it puts it into a list that Python can make use of. So once we have this list, we continue writing our Python script, and you can see here we're taking the variable which has got all our coordinates in it, and we're writing that into the Python script as well. And now we're writing all the values from the Python script variable into this temporary Py file, and that then allows me to run my Python file direct from Surpac. Now this is the new part to this. We now have a command here called SCL Python Executor, and I just put in file as the type, and then I just nominate the Python file that I want to run or execute, and Surpac will go away and run this. So in this particular instance, this Python file is going to run a what we would call a procedure or a definition. So it runs this process polygon to CSV. This expanded polygon contains all the coordinates that I've gathered using my TCL process, and it's going to put the expanded polygon into this CSV file name, which is called expanded polygon CSV. So it runs this process, outputs a CSV of the expanded polygon coordinates. I can then open that expanded polygon coordinates using TCL again, and I iterate over every single line in my expanded polygon CSV, and I create new points. Okay, and then it gets to the end of the while loop, and if I haven't pressed escape, I can then go ahead and select another polygon for expansion. So the real magic for this comes down to this new command that we've added in 2025 refresh 2 to allow me to call these Python files direct and run them as part of a TCL macro. So it's very, very flexible and very, very helpful for a lot of things that we can do. And you're only really limited by your imagination here, because you saw, or you will see soon, we can use AI to create Python scripts for us, and we can incorporate those with our current TCL scripts to create something similar to this. So for this next example, I want to show a pre-existing macro that I'm going to create a Python script for the charting that this macro does with Java at this point in time. So all the macro does is takes design collars for a blast design and the actual pickup of those collars. And when I'm in graphics, I can compare those two. And the macro spits out a Java chart. So you can see that I've got a histogram here of how many holes deviate by what amount. And you can see the table that's listed there. So again, it's just listing out how many holes deviate and the actual deviation percentages themselves. So that macro, the same macro, also outputs a CSV file. And this came in handy because the CSV file was originally meant to just paste onto another report. But what I've been able to do with the CSV file is give it over to some artificial intelligence, so in this case Grok. And I've just said, Grok, this is what my CSV file is of. I'm wondering if you can sort of create a Plotly chart for me in Python. And I want a histogram for the number of holes, and I want a pie chart for the deviation percentages of those holes. It goes away and creates a .py, a Python file for me. And I can basically just drag and drop this py file into graphics, and it utilizes the CSV file that my macro was already producing to create charts like this. So I've got a hole count by deviation range, and it lists it out in nice order there, 100 mil to greater than 700 mil. And then it's also given me a pie chart, which is the deviation percentage distribution. And you can see very, very quickly and easily, most of my holes are within target range, and you can see a small slither of the pie where they're outside of target range. The beauty of this as well with Plotly is it allows me to take screen captures or images of the actual charts. So I just click on this download plot as a PNG. 2 seconds later, I've got a nice chart in PNG format that I can then paste onto any report that I want to as well. So the HTML can be sent to people, and also the PNG file can be used for reporting. So it's very, very helpful in that regard. Now, if I jump back in here, you can see the macro also gives me color-coded holes with the deviation listed above the hole. Which is also very helpful. And if you want this macro, just let me know and I'll forward it to you. So this next example that I'm going to show you is a variation on what I've already demonstrated. And it's where we have the use case of running a TCL program, creating some variables, and then passing those TCL variables through to a Python script at runtime. So it varies in from what I've shown you previously, where I've actually created the Python script at runtime. This time around, I'm calling an existing Python script and just passing TCL variables to it. So if I have a look at the TCL component, this is what would be executed first. I'm creating a Python, well, I'm setting a variable called Python file to be the actual Python script. You can see it just here. And I'm creating a TCL list. These are just a list of names that I'm going to pass through to Python. Here's another variable, TCL variable, which stores this data CSV, some sort of CSV that I want Python to interact with, and an integer value and a real value, just to show you some of the differences. And down the bottom, I am using the new SEL Python Executor command, and it's going to execute the Python file. And these are the variables that I'm going to pass through to it. So take note of this. I've got 4 variables that I'm passing through to my Python script. So if I flick across to my Python script and have a look at that, we can see that straight away it's importing this variable sys for the module to work. It's going to count the number of arguments that are actually coming through. Okay, so system arguments, it prints those out for me. The first argument was my list of names, so that comes through here, argument 1. The CSV file was in the argument 2, integer value was argument 3, and the real value was stored in argument 4. Okay, so then it just uses some Python code to print the names, because it's now stored in this names variable. Now, the Python string names comes in there, so using a split command to actually split them out properly and then looping over them one by one, which you can see. Now we can print out the name of the CSV file here. We're not doing anything with it. Printing out the integer value and printing out the real value, and then it's just saying that it's complete. So let's have a look at that and how that would run. So I jump back into Surpac. Remember that I'm running my TCL code. Okay, now that's passed all those variables through to Python, and you can see that's the first list that gets called. Then it splits it, so you can see each name line by line, and it's just printing out what value was stored in argument 2, I think it was. Argument 3 was the integer value, argument 4 was the real, and then it's just printing a message window saying it's complete. So this is another way that we can utilize the new command to actually execute Python code. We're executing the TCL first and passing those TCL variables through to the Python code at runtime. So to finish off, I thought we'd have a bit of a look at some examples just to spark the imagination of what can be done. So here's one that takes some data and performs kriging on it to essentially give you uniform sampling throughout and charting that up there. So that's just another charting type Python script. Here's one that demonstrates some cut and fill. So I have a plane here and some areas of cut and areas of fill, elevation legend over here and a cut and fill legend here as well. You can rotate the charts around. And again, this is another Plotly chart. Got another example here of some charting. So it's at raw at the moment. Let's try log. Let's try linear. We can interact with the legend over here, turn things on and off. And again, we've got the option there to download as a PNG. So really, really flexible options with Plotly from the Python library. So a couple of other options that we have, or examples that we have, is draping georeferenced JPEG files. So this is quite common when you get JPEG files from packages like QGIS or Agisoft or Propeller. And the JPEGs are good because they're highly compressed and actually very small. So this one here is 1.1 megabytes. And the SDM that I want to drape it on is not that big, but reasonably detailed. So the macro will create an RGF file for me. And if you're familiar with Surpac, the RGF file is what links the JPEG to the SDM or DTM. And you can drag it in at any time and see the draped image. So I'll select JGW file, the JPEG and the SDM, and this pillow library is where the magic happens, and it'll investigate the JPEG and work out the pixel sizes and then do the draping for me, or create the RGF file and do the draping for me. So then we end up with a draped image, three-dimensional, and that saves a lot of hassle about registration points or registering points in graphics. Another thing we can do here is string transformations. And I'll just show you the form. So it looks like this. So it allows me to choose a grid system that I want to go from and to. And I can add to these grid systems as many as I like. And all I need to do is go to this website here and look up the EPSG code and then put it into the database of this macro. And that'll allow me to do the transformations. Now, if you want the high precision transformation, you need to have the associated GSB file, which can be, for the case of MGA, can be downloaded from GitHub. And down the bottom is just a label to tell you the EPSG code you're going from and what you're converting it to. So another macro that you're welcome to have, just let me know. So in conclusion, I'll just summarize the main points. So essentially, Surpac 2025 Refresh 2 will have a new command called Sci Python Executor. Now that's going to allow you to both execute Python scripts from inside TCL macros, and it's going to allow you to pass TCL variables through to Python scripts as well. So on top of that, we also saw how we can actually use a TCL wrapper to wrap our Python code at runtime, and that's another way of passing TCL variables through to Python scripts. Very effective method. We also saw how we could generate Python code using some simple AI prompts and adding those to our TCL macros as well. So I hope you enjoyed the presentation and got something out of it. And please feel free to ask me some questions. I'm going to be hanging around for question time.